Hello everyone and welcome back to the Robot Whisperers. In episode 1, we demonstrated the value of using 3D digital manufacturing software to create a 3D work cell layout. Then we showed you how to add kinematics to the work cell to enable us to start creating a 3D simulation. This demonstrated how 3D can help you better utilize the space available for the work cell and make any CAD geometry come alive to interact with other devices in the work cell. This enables companies to greatly reduce the time and cost of putting a manufacturing system into production. Now let's continue our journey into the world of robotics. In episode 2 of the Robot Whisperers, we're going to talk about the robotology of arc welding. We're going to talk to you about how companies use simulation to program and validate robotic arc welding work cells.
We'll show how to create auxiliary axes on the robot. That is, we'll combine the virtual robot with the virtual gantry and part positioner, so we'll have an 8-axis device. Then we'll show how we can use the features of the CAD geometry to create complex robot paths for the robot to weld.
This enables you to create a huge amount of robot locations quickly and accurately. We'll also show you how to orchestrate all of the work cell operations to create the simulated production cycle. This turns our work cell into a symphony of motion.
This episode will show you how you can use 3D simulation to choose the right robot model, the correct robot placement, the right torch for the job, and put it all together in the proper configuration to offline program your robots to get it right the first time. So let's get started.
Today, most robotic arc welding cells use a part positioner, a gantry, or both for production. These devices allow the work cell to be flexible enough to do a series of welds. They also allow for a variety of parts to be welded. The trouble is when the robot programmer has to manually program these three pieces of equipment. Manual programming is complicated, not to mention programming the work cell using a teach pendant can be very time-consuming.
Starting with a completed layout, the first thing we'll do is mount the robot to the gantry. The robot will come from the Delmia Robot Library. The gantry can come from the Delmia Library, or you can create it from the CAD data. Next, we'll attach the torch to the faceplate of the robot. When the torch is built, we open it in Device Builder, not to add kinematics to it since it has no motion, but to add a tool point location to it. This is added so when we attach it to the robot, the tool point location gets added to the robot parameters automatically as its tool center point.
Now that the robot is defined with its tool center point, we can attach the part to the positioner and use the software to start creating weld paths for production. So using the software to attach the robot, we first pick the robot, then the gantry. Now we have to define where the auxiliary device is attached.
An auxiliary device could be located at the base of the robot, like the gantry, on the floor, like the part positioner, or it could be at the end of the robot arm, like a weld gun.
Combining these devices allows each axis to be considered as part of the robot. So all the positional data of the robot and the aux axis can be communicated to the robot on the floor through offline programming. Now the work cell is ready to start creating robot paths. Delmia uses the features of the CAD model to create these paths. There are several methods to do this. You can create a path on intersecting surfaces, on a curve, or on intersecting parts.
Here we'll use the intersecting surfaces method. Delmia calculates the angle between the surfaces and then bisects that angle. You can create a start and end point only, and this works great if you're welding in a straight line. You can create a known number of robot locations, say 12, and it will equally space them, or you can have the system identify a sag value around a curve and apply that value, so your accuracy of welding around a curve can be very high. Once we have the robot paths created, we can go into the robot teach page and apply ingress and egress locations.
You know, Tony, another important feature of the software is that it enables the user to customize the way the system creates these robot locations. This saves a tremendous amount of time programming welds on complex workpieces.
That's a good point, Mike. So let's talk about the benefits of what we've seen. The system's capable of creating a lot of robot locations very quickly. Imagine that a programmer is working on a part that's extremely large like this one. Using the teach pendant takes an exorbitant amount of time to create all those robot locations, especially if it's a very complex part where you can't copy or mirror the locations. The simulation with offline programming allows you to quickly create hundreds of robot locations and create them more accurately than you could with a Teach pendant.
The Robot Teach page is where we can manually add robot locations to a robot path. You can insert VIA locations either before or after for ingress and egress to the welds.
This is also where we can dress the path with specific robot information for the robot to follow the path. We can adjust the speed and accuracy of the robot program. We can also change things like interpolation style, which affects the motion. The wrist configuration, tool point, and U-frame can also be changed easily in the program.
Once the robot welding path is created, we can program the gantry. The gantry values can be calculated in a number of ways.
You can provide a constant offset value, and the system will calculate the gantry position to maintain that offset from the center of the robot to the robot location. You can enter a fixed value where the robot rail will maintain that position you input, or you could set it to minimize motion.
Here, Delmio will calculate the gantry value based on the minimal motion needed to reach each location. The part positioner can now be programmed in the simulation.
The idea in arc welding is to keep the weld as flat as possible. Since molten metal flows with gravity, it's a good idea to use a part positioner to keep the weld where it belongs.
Delmia gives you several options to program part positioner values. You can program it to be flat, vertical, or horizontal.
It can also be user-defined, where the system will align the weld points according to the vector that the user inputs. Once the system calculates values, it informs the user of reachability of all the weld points in the weld path.
Now that we've defined the robots and laid out the weld paths, Tony, why don't we take the time to show them how we bring it all together? We integrate everything we've created so far by using work cell sequencing. Work cell sequencing allows you to arrange the order of execution in the simulation. It lets you easily orchestrate the order that your weld paths are simulated.
To orchestrate a work cell simulation, we program it in a PERT chart. In the PERT chart, we can arrange the sequence of operations for the entire work cell. Here we can execute device tasks as either in series or in parallel operations. If we want the work cell sequence to execute differently, we just delete the arrows and redraw them in the PERT chart.
Tony, I think this would be a good time, now that we've shown the capabilities of virtual programming, to summarize some of the key points our audience should take away.
Okay. Well, we saw how easy it is to program the rail and positioner. This saves a lot of time for the programmer, especially when there's multiple weld paths. Since we're working in a 3D environment, we can examine the effects of different programming methods. We can visualize different production scenarios, and we can see their effects on the work cell cycle time. This really increases the engineering quality when developing a work cell.
Now that everything is put together, we can do some engineering studies on the work cell. One of the primary focuses of performing engineering studies when programming a work cell is to avoid collisions.
Collision detection allows the engineer to check the robot path under motion to see if the robot or its end effector collides with any other object in the work cell. It's a primary focus because robot crashes are one of the most costly mistakes that can happen in a production startup.
Collision detection is also important because it lets us examine the physical relationships between objects in the work cell.
That's right, Mike. Like between the part and the end effector, or between the end effector and the tool fixture, or even the product, the end effector, and the tool fixture all at the same time.
We'd like to thank everyone for tuning into this episode of the Robot Whisperers, Robotology of Arc Welding. Now you can see the value of how quickly and easily you can program and validate an arc welding work cell using simulation. This greatly reduces time and cost when using robots in a production process, and it greatly reduces the risk involved when launching a production work cell.
Thanks again for joining us, and we'll see you in episode 3 of the Robot Whisperers, Robotology of Spot Welding.